So let's look at this chemical here. This is the organic way of doing it. There's technically a C right here that's hidden. Looking at more from lower level. And usually we omit extra lone pairs and stuff. But basically this oxygen has an additional electron. The proper way would be to put brackets around it. It has many different formulas. The most common way of writing it is CH3COO negative. Yes, it is. See a carbon with a carbon. Another way you see it is CH3CO2 negative. Or sometimes they combine them all together. Like that. What is the name of this compound? Yeah, this is the way it's usually always written. To illustrate structure of the atom, they wrote it all the way out because it's really this one oxygen on the molecule that's doing everything. Everything else is stable. It's this one oxygen that's going to dictate the entire reaction. This is an important one to have memorized. It's acetate anion. So what would acetic acid be? The formula for acetic acid. So acid means that we're going to have an H plus ion, cation mixed with an acetate anion. And they react together to get you this formula. Technically, you will always see the formula written like this. This is the way it's usually written. Sometimes you might see it written like this. And sometimes very horribly, you'd see it written like this. Out of all of them, that's one we're definitely not doing. Why is this so strange? The other class immediately pointed out that we didn't group the carbons together in oxygens. That's just acetate being weird. But why is the preferred way this chemical is written weird? What's different from how I read it here? So we usually always put cations in the front, anions in the back. And even though I'm going to teach it using this, I really should teach it using this, because this is the way you always see it. But in this class, we always put cations first, anions last. The reason why is that's just the convention everyone writes it in. I'm also not going to use this version of it either. This is the way you'll always see it. So this structure looks like so the only thing doing bonding is this oxygen. There we go, acetic acid. What's another name for acetic acid? You have it in your kitchen.
I don't know where that came from. Just don't ask.
I know where it came from. Buried in the back of your mind, I know exactly where it came from.
Where did it come from?
I'll get to it here in a little bit because I'm going to ask that question and you're going to immediately scream baking soda.
So it makes sense, right?
Yes, yes.
Oh, heck yeah, guys. Omega Power Rangers.
But what's the name of this? What's an acid we use in the kitchen? Vinegar. This is vinegar. So, the question you should have, in elementary, made a chemical reaction. Or if not elementary, junior high. Yeah, it's usually around 6th grade, which used to be elementary.
Yeah, I think
I'm still not used to the fact that 6th grade is now considered junior high.
next grade is the last grade to.
But between vinegar and what? Baking soda. Yes. So, vinegar, the technical chemical name, is acetic acid. And I'm going to put the H in front, so we have always, by convention, cations first. That is H, CH3, and that should be a C. What is the chemical name for baking soda? Soda is a short name or Latin name for a chemical. Sodium. Be bicarbonate. And what's the equation for sodium bicarbonate? Na plus. Carbonate is CO3, 2 negative. We're going to add onto it the bi represents the H. So that combines to HCO3 negative. The plus charge is going to cancel out one of the negative charges. This is a 1-to-1 ratio. So sodium bicarbonate is NaHCO3. So what is the reaction? And this one's more complicated than what we've done before. I didn't explain it last class very well. Yes? Mm-hmm. But I'm re-explaining it better now. So, first of all, I really hate seeing the H in front, but I'm doing it for a particular reason. Is this soluble in water? Vinegar. Is vinegar soluble in water? So, one of the rules. Almost all acids are soluble in water. Let's look at our rules to see if they match any rules to begin with. So, this is a list of soluble elements. There is no exceptions. Acetate, anything containing acetate is soluble in water. Alright. Then baking soda. Is that soluble in water? So we don't have a bicarbonate, but we do have a carbonate. The hydrogen doesn't really affect the solubility. So carbonates are insoluble in water, unless they're combined with an alkali metal, cation. Sodium is an alkali metal. Therefore, it meets the exception and thus is aqueous. And what would be this reaction? And keep your mask on. So, we have two ionic compounds. This is the part I didn't explain well on the for the previous class. But I figured it out. So, what type of reaction is this? We have two ionic.
Like the synthetic.
Mhm. We have two ionic compounds being mixed together. We have two compounds that have a cation and anion. Two parts. Double displacement. So the cation here is going to get the anion here. So that would make sodium acetate. If y'all remember my supersaturated solution where I dropped the crystal into it and it instantly froze? That is this chemical. This is how you make it. Sodium acetate. If you want to go home and make some of your own, get some vinegar and baking soda, mix it together, and somehow filter off everything and do it perfectly, and you can get some sodium acetate to play with. Without buying it online, but I can tell you already, every single chemist in the entire world just buys this in bulk online. No one ever makes it because this is made in tremendous bulk. And we're going to take the cation here and the anion here, and that makes H2CO3. This is where I told the class, because I gave them the full thing, this right here, you have to know something special about it. What is this? What's the name of this? It's technically, so we had H plus, and then we had a HCO3 negative. What does this scream to you? What should you know is part of the name? You should be screaming to you something part of the name as soon as you see one of the ions. What's special about one of the ions? H plus. What does that mean? What does it mean when you have an H plus ion? It's the definition of it. It's an acid. Definition of an acid. So what would be the name of this acid? Well, we have a hydrogen plus, I'll tell you already, this is where it's weird. The other H is going to, this is really going to do H plus and CO3 2 negative. This H is going to be combined like that. Whenever you have two hydrogens, this hydrogen is not going to want to stay attached to this one. But what's the name of this? CO3? Carbonate. So what's our acid naming rules? If it ends in 8, then we put an ick on it. Carbonic acid. What is carbonic acid? Gotta drink it every day. It's carbonated water. Does it stay as carbonated water, or what happens to the carbon? Or the carbonic, or carbonate? So this is where you have to know something special about this formula. This carbonic acid is unstable. It decomposes. What does this decompose into? So above negative 80 degrees Celsius, this spontaneously, so above negative 80 degrees Celsius, in the presence of H2O, this is going to break up. Well, what do you think? What's a common formula? What's carbonated water? Water and CO2. So this is going to very quickly decompose. So our overall equation is this. Which, this is the volcano experiment. What is produced during the volcano experiment? Gas. This is our gas that's being produced. Water is a liquid. Is this soluble? Sodium acetate? That was literally my super saturation thing where I dissolved a ton of it in a little bit of water. Anyway, anything with acetate is soluble. So this would be aqueous. So we've written our equation out. We know the equation for vinegar and baking soda. Is this balanced? What should be the subscripts in front of it?
Yeah, 5, 9, 10, 8. Yeah, 5, 5,
How many carbon do I have on the left side?
3,
3. How many carbon do I have on the right side?
2.
You sure?
Oh yeah, no, not 3.
1, 2, 3. 1, 2, 3. There's 5 hydrogens. 1 plus 3 is 4. 5. So 3, 4, 5. And 5 oxygen. This is indeed balanced. So this is the overall equation for making a volcano experiment. So what this equation says is if we take one molecule of acetic acid it reacts with, it's the plus sign, one molecule of baking soda to make, that's the arrow, one molecule of sodium acetate and one molecule of water and one molecule of carbon dioxide. So one molecule of this reacts with one molecule of that to make one molecule of this, this, and this. That is what this equation says. So when we react things, do we do it one atom at a time? That's too small of an amount. Why don't we increase the number to 6.022 times 10 to the 23 molecules? That's a better amount to be working with. How many molecules? What does this represent?
All I know is in the beginning, wasn't it, didn't it start with 80 something?
This is Avogadro's number, but what does Avogadro's number represent?
Can I get grams in the mold?
It's 1 mole. 1 mole is like a dozen. 1 dozen would be 12 molecules. 1 mole is 6.022 times 10 to the 23 molecules. So instead of working with 1 molecule, let's actually increase this reaction to a whole mole. We're still counting. These are all counting numbers. It could be 1 dozen, but a dozen is still too small. Instead, let's move this up to a mole. So, let's say that I did 100 billion moles of vinegar, or let's just use a word we're common with, 1 billion tons of vinegar, with 1 mole of baking soda. How much water, CO2, and everything is produced? Well, we know from the equation that 1 mole of this and 1 mole of this gets 1 mole of that, 1 mole of that, and 1 mole of that. If we had a billion moles, a billion tons of this, it doesn't matter. As long if we only have 1 mole of this, right? So 1 mole of this will react with exactly 1 mole of this. So if we had, for example, 1 billion moles of this, it doesn't matter. 999,999,999 moles will just stay there unreacted, while 1 mole will react with this. Make sense? So we call this being an excess. When we mix something together, we're going to usually not have it exactly 100% lined up. Our baking soda in this case would be our limiting reactant. It limits how much will be produced. Well, this would be our reactant of excess. So let's find the molar mass of everything. So the molar mass of acetic acid, and I keep leaving that off, this extra carbon. So we have 4 hydrogen, we have 2 carbon, and we have 2 oxygen. So looking at our periodic table, we do 4 times the molar mass of hydrogen plus 2 times the molar mass of carbon plus 2 times the molar mass of oxygen. Add them all together and we get the molar mass of acetic acid. It's 60.05196 grams of acetic acid per every 1 mole of acetic acid. That's the molar mass. Let's do the molar mass of baking soda. Which is sodium bicarbonate. So that would be 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygen. So it'd be 1 times 22.98977. 1 times 1.00794, 1 times 12.0107, 3 times 15.9994, add all those together, and we get 84.00661 grams. Mute your phone. I put it on silent, not.
Can I take this? It's my sister.
Mm-mm.
No, we just, that's easy, I'm not gonna call back, but that would have been like something.
Yeah, be quick and then put your phone on silent.
I don't think that's everything.
And let's do CO2. Or, not CO2. Um, sodium acetate. So it's 1 sodium. (12.0107), 3 hydrogen, and 2 oxygen.
I thought the one that she was trying to.
They're still calling me,
Put it on silent and put your phone up.
they're calling me twice.
They should call the school if it's an emergency. So that equals 70.02309 grams. Put it up.
Trying to fix something, I'm not gonna call.
Water. Which I'm just gonna write. I didn't calculate it last time. Ran out of time. So that'd be 1.00794 times 2 plus 15.9994. So that's 18.01528 grams H2O per 1 mole of H2O. And then molar mass of CO2, which I will just write. It is 44.0095 grams CO2 per 1 mole CO2. For the rest of this, I just go around these. That's basically 60. That's basically 84. That's basically 70. That's basically 18. That's basically 44. So what this tells us, we know 1 mole versus 1 mole versus so on. So that tells us, basically, if I have uh, 60 grams of pure vinegar, has to be pure, which is impossible. Or not impossible, but basically extremely hard. And then if I have 84 grams of NaHCO3, then I will expect I will get 70 grams of this sodium acetate, and I will get 18 grams of water, and I will get 44 grams of carbon dioxide. Makes sense? So 1 mole to 1 mole to one, gives you 1 mole of that, 1 mole of that, 1 mole of that. So here's the question. If I mix 100 grams of pure vinegar with 100 grams of pure baking soda. How much CO2 is produced? And I'm just going to solve it for all of them. Nope. So this is assuming 1 mole to 1 mole. I'm not using 1 mole. I'm using a little over a mole. 100 grams of vinegar is, I can actually tell you, that's basically 1.6 carried moles. And this is basically 1.19 moles. So I'm using a little bit more, but this is just a ratio problem, related ratios. But before you do that, we need to figure out what if I change this problem? What if I mixed 1 billion tons of vinegar with 100 grams of baking soda? How much CO2 is produced? Did the problem change at all?
No.
No. Maybe. Paul, keep your eyes open. So the question is, which one is in excess? Vinegar or baking soda? So which one will get to 100 grams first is the question. If I keep increasing these two numbers at the same rate, which one will get to 100 grams first? Baking soda. So baking soda is our limiting, or I should put it down here. So baking soda is our limiting reactant. It limits because only 1 mole of baking soda will react with 1 mole of this. So only 1.19 moles of our baking soda, I'm putting 1.19 moles in. That means only 1.19 moles of vinegar is going to be used because it's a 1-to-1 ratio. If I put 2 moles of baking soda in, then it will only be able to react with 2 moles of this. And to figure out the ratio, yes, homework. Oh, so that's the homework. And just So 2 possibilities. I'll work through both of them. One, we're going to assume vinegar is in excess. So that means we're going to change. So the ratio is 60 grams vinegar to 84 grams baking soda. And I'm going to change the baking soda to 100 grams baking soda. And I'm going to have now X vinegar. What would X be? So this is just a cross multiplication. 60 times 100 is equal to 84 times X. The X is being multiplied, so I divide by 84 to get rid of it on that side. And I get that my X amount of vinegar is equal to 71.43 grams. If I do it the other way, if I assume wrong, and let's say I assume that I get the vinegar to 100 grams. Doing this calculation, crisscrossing, you would see that it would require 140 grams of baking soda. which is a contradiction because I said I'm only using 100 grams of vinegar and 100 grams of baking soda. Obviously, we can't use more baking soda than what is specified. So that means vinegar is in excess and baking soda is our limiting reaction. So what is going on is out of our original thing, 71.43 grams of baking soda is reacting with 100 grams of vinegar, is reacting with 100 grams of baking soda. So 71.43 grams of acetic acid is reacting with 100 grams of baking soda. We can figure out what's left. By the way, if only this amount of acetic acid is being used, it means we're also going to have some excess left over that didn't react. We would have 28.57 grams that is unused. That'd be leftover. So this is just a related problem. It's just going to be mostly this. We know the ratio is going to be, I like using this one. It's so it's usually 84 grams, but we're using 100 grams. Usually what is made for 1 mole is 70 grams of sodium acetate. What would the X be? Again, it's just simple 100 times 70 is equal to 84 times X. Move the 84 over here, and we see that X is equal to 83.3 grams. So by mixing these together, I get 83.3 grams of sodium acetate. Again, I know the ratio is for 1 mole is 84 grams of baking soda, but I'm using 100 grams of baking soda. If I used 84 grams, that would usually give me 18 grams of water. But what would it be for the 100x? Same thing. It'd be 100 times 18 divided by our 84. Tells us how much water is produced, which would be 21.43 grams. And to answer the original question, so it's for 1 mole is 84 grams, but we're using 100 grams of sodium bicarbonate. Usually for 84 we get 44. What we get now is we solve for X. So 100 grams times 44 equals 84 times X. So that'd be 100 times 44 divided by 84. Gives us 52.381 grams. So to answer the original question, if we take 100 grams of pure vinegar, react it with 100 grams of pure baking soda, we will get 52.381 grams of carbon dioxide. Make sense? So this was a simple case because all the subscripts is 1. I recommend this YouTuber if you're interested about chemistry and learning. It's called Neil Bread. You'll see he goes through making lots and lots of weird things, or common things, using weird. He's a chemist. Like he's made. Let me see if I can find this where I guesstimate. Yeah, he made an artificial sweetener using his own pee. So he's done some weird things, but I think that's like the weirdest thing he's ever done. But he's really, really good. He's really, really good at doing chemistry, and he goes through all the steps and shows you exactly how you can actually make things using common chemicals. Of course, he has his own lab and stuff, but you'll see him talking about throughout this entire process. He'll end up, like, for example, theoretically, he should come up with 100 grams, but he ends up with 50 grams, and he'll tell you he has a 53% yield. You'll find in the real world, chemistry experiments don't work out exactly like this. We're going to end up losing some of the chemicals. Sometimes they don't react. Because in order for this to 100% work, we have to get every single molecule to react with every single molecule. And just like when you put sugar in tea, even though theoretically it should all dissolve, you notice that you have to stir it up to force it to dissolve more. And after stirring for a long time, yes, you get more to dissolve. But sometimes you just can't get all of it to dissolve because it's going to take a really, really long time to all react or all fully dissolve. Same thing happens with the reactions. There's also some other things that can go on. So, for example, you needed to know that this breaks down, but this may not always break down. We should expect some of the CO2 to stay dissolved in it and stay as carbonic acid. Eventually, it will all go flat, and the CO2 will bubble out, just like a regular drink, but some of it will stay dissolved as it takes a really, really long time for all the carbonation to leave it. But this is basically what we're going to be working on. Figuring out how many grams to react with everything. So it's basically expanding. Another thing we need to do is you will not find 100% vinegar. You will probably find 4% vinegar. How does that change it? You need to know how many moles per liter are actually in it, so that you can measure out. Maybe it calls for 1 mole to 4 mole ratio. And let's say you put 1 mole of this, in which case you need 0.25 moles of vinegar. So if the ratio, if you, then you need to calculate how many milliliters are needed to get 0.25 moles. And that's more what we'll be working on. So acids are usually given, it's called molarity. Molarity is moles per liter. So we could have like 5 molar liquid. What this tells us is we get 5 moles per 1 liter of the liquid. Which means if we have a full liter of it, we'd have 5 moles inside of it. But 1 liter, doing a whole reaction with 1 liter, we're going to more likely have to turn this into milliliters, which is equivalent to 5 moles per 1,000 milliliters. And then shrink this down, so if we only need 100 milliliters, that'd be 0.5 moles, a half a mole per 100 milliliters. And then if we have something with 10 molarity, that's capital M, and we want to do 1-to-1 ratio, then that would be 1 mole per 100 milliliters, which means we need to convert this into 0.5 mole per 50 milliliters. So if we want to do 1-to-1 ratio, we need to do 100 milliliters of this with 50 milliliters of that to have it 1-to-1 without having excess. And that's what we'll be working on. And that's it for today. If you want to go figure out what was up with your phone, you can.